Welcome. Let's have a look at the following counting problem. Here it is. How many different ways or patterns are there to color the squares of a 2x2 chessboard using only the black and white colors? So what I did is I went ahead and created what I thought were all the possible colorings. And in fact, to make sense of it, I would like to give each one of these a name. So let's call the first coloring as C1, where all the four little squares are colored white. And then the next one, C2, C3, C4, C5, C6, coloring 6, coloring 7, coloring 8, coloring 9, coloring 10, coloring 11, coloring 12, coloring 13, coloring 14, coloring 15, and coloring 16. Even though it doesn't look so, this is four little squares all colored in black. And you would sit back and say, hey, the answer is 16. However, you scratch your head and you realize, wait a second, some of these colorings are essentially the same. They are not really distinguishable. For instance, one can obtain coloring C3 using coloring C2. All you do is you rotate coloring C2 pi over 2 and you get C3. And in a similar way, you can obtain C4 using C3 or C2. For instance, if you rotate C2 coloring, the second coloring, by 180 degrees, you would get C4, and so on. So when we say essentially different coloring, so we really mean that we shouldn't be able to obtain a coloring using another one by just a rotation, or in fact a reflection. When you think about it, if this chessboard is transparent, so from the bottom you can see the colors and so on, so it's possible as well. In fact, what I want to do is, in this case, I want to solve it up to, so essentially different colorings up to rotation and reflection. And it's easy to modify this question considering only rotations or only reflections, or like I said, in this case I'm doing both rotations and reflections. Therefore, there are essentially 6 different coloring patterns in here. Basically the coloring of C1, the colorings C2, C3, C4, and C5. Then we have coloring C6, C7, C8, C9, followed by coloring C10 and C11. We also have coloring C12, C13, C14, and C15, which are essentially the same, and finally coloring C16. So ultimately we would have only 6 different coloring patterns on a 2x2 chessboard using only black and white colors. But now the question is, how can we generalize this result, and so that it applies not only to a 2x2 chessboard but to a 4x4 or an 8x8 chessboard as well. So in that regard, we need some theory. The general theory is from group theory, the study of symmetries of objects, and particularly there's a very useful result known as Burnside lemma, and we will be using that lemma to actually sort things out. So let's consider the group of symmetries. So let's call this group as G, and we need to figure out how many symmetries are there. So we claim there are 8 symmetries for the square, and these symmetries are the identity, basically do nothing, and then the rotations, the 3 potential rotations. A would represent pi over 2 rotation, B would represent rotation pi, let's say clockwise, C would be rotation 3 pi over 2. So, and E, rotation 2 pi would be E identity again. And then we would have 4 reflections, basically the reflection across the horizontal, the reflection across the vertical axis, then the reflection across the diagonals, right, R and S. And just to be more precise, what we can do is symbolically I can put this to reflect horizontal, vertical, diagonal, really like from top left corner to bottom right corner, or the other diagonal. So these are the 8 symmetries, group members of the group of symmetries of the square. And now I will have 2 back-to-back definitions followed by 2 theorems that will ultimately lead to the description of Burnside lemma. Let me create some more space underneath. There you go. So the first definition, let me make it in blue color. So this is a well-known definition for the orbit. So we say that colorings that can be obtained from each other are said to be in the same orbit. So we can obtain a coloring from another coloring using a group action on this set of colorings. We said that these 2 colorings are in the same orbit. So definition for orbit: consider 2 colorings X and Y in our set of colorings. Let's call the set of colorings as X. We claim that OX is equal to OY, meaning X and Y are inside the same orbit. This can equivalently be represented as X is indifferent under group actions to Y, or even alternatively, you can write it as OX, the orbit where element X lives, is equal to all the other colorings that can be obtained by applying a group action. So one of our symmetries to our element, where our G, little g, the symmetry comes from the group itself. So that's pretty straightforward definition. And another definition, and that's an important one obviously again, that's the definition for stabilizer. So we say that the stabilizer of X, or you can even write it as S sub X, contains group elements that fix S, or in another way, S of X is the set of group elements G in G such that when applied to a coloring, we get the same coloring. So what are those group elements? Those symmetries, when applied to any coloring, you get the same coloring. So for example, consider the case, e.g. consider the case of say coloring 1. What would be the stabilizers of coloring 1? Identity would be one of them, obviously. If I apply a 90-degree rotation to coloring 1, remember coloring 1 was all 4 little squares are colored white, so therefore nothing would change. So 90-degree, 180 or 270-degree rotations will not change anything. as well as any rotation, again, will leave our coloring the same. So therefore our coloring is fixed under any of our group actions. So therefore the stabilizer of C1 is basically the whole thing, the whole group. In fact, in a similar way, I should be able to obtain the stabilizer for any coloring in our set, and that should be pretty straightforward. So in the next video, I will go ahead and create those stabilizers one after the other, and then we can come up with our two theorems. So we're done for now.